Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Question 28 states that the water that cools a reactor core enters the reactor at 216 degrees Celsius and leaves at 87 degrees Celsius. The water is pressurized, so it does not turn into steam. So we don't need to think about any latent heat of vaporization or anything like that. The core is generating 5.6 times 10 to the 9 watts of power. Assume that the specific heat of water is 4,420 joules per kilogram per degree Celsius over the temperature range stated above, and find the mass of water that passes through the core each second. So how much water passes through the core with these given parameters to us? So based on what we know that the energy produced when we're dealing with the change in temperature, we use the expression of the energy equals mass times the specific heat of whatever object you're dealing with, heated water, multiplied by the change in temperature. Here we're looking for mass, so we can rearrange this equation, Q over C delta T. But we're not really given energy here, we're given watts, which if you remember, 1 watt is given as 1 joule per second. So we can take the term we have for power and simply just represent it as joules per second, which will be useful because if you want a value of kilograms per second, right, because that's what it's asking for, how much mass each second going through the reactor, then we have all of our values and we can simply plug in from there, right? So we have the energy, which is just the power, we can represent it, 10 to the 9 joules. Oh, I said watts, but it should be, joules per second, as we stated. Over C, which we know, 4,420 joules per kilogram per degree Celsius, and multiplied by this change in temperature, 287 is our final, minus 216, our initial, all with degrees Celsius. Just double checking our units. Our joules cancel, degrees Celsius cancels out here, and we're left with 1 over seconds in our numerator and 1 over kilograms in our denominator, which would give us, just to verify, it would be kilograms per second. So again, we took this Q to equal power times time, essentially, but we're leaving it in terms of power or energy rate. So we do have kilograms per second, and just plugging in these values, we find that we get 17,845 kilograms per second. But looking back at our givens, we're only given 2 significant figures. So we can say that's 1.8 times 10 to the 4 kilogram per second. That'd be our final answer.